in Chapter 5 we were using a geometric method to solve linear programming problems. Fairly easy method to use, fairly nice and friendly, but it had the downside in that it only worked for linear programming problems with two variables, because we were stuck to 2 dimensions with our geometric approach. We want to expand on that. We want to be able to solve linear programming problems with more variables, and to do that we introduced something called the Simplex Method. It's really an algorithm that a lot of computers use to solve linear programming problems. It's a fairly long algorithm, and unfortunately we're going to have to limit ourselves to linear programming problems of a particular form. But even so, we'll be able to introduce more variables. So in this thing I have written by me that we'll talk about in a second, I have 3 variables there. And we'll ultimately just develop more practice in converting these real-world applications, these word problems, to mathematical models and then solving the associated linear programming problem. So here's what we're going to look at. In Chapter 6 we'll be solving what are called standard maximization problems in standard form. Like the following problem that I have behind me, which is maximize p equals 50 times x sub 1 plus 20 times x sub 2 plus 3 times x sub 3. And you'll notice here that I'm calling my variables x1, x2, and x3 instead of x, y, and z, because we're going to allow many variables here. You run out of letters pretty quickly, so once you start going beyond 2 or 3 variables, you just you start subscripting things instead. So instead of x and y, I've got x1, x2, and x3 for z. Alright, so we want to maximize this function subject to the following constraints. X sub 1 plus x sub 2 plus x sub 3 is less than or equal to 12. 2 times x sub 1 plus x sub 2 is less than or equal to 30. And x sub 2 minus x sub 3 is less than or equal to 5. And then I have down here my non-negative constraints. x1, x2, and x3 all have to be non-negative, bigger than or equal to 0. So what makes this a standard maximization problem in standard form? Well, 1, we're maximizing a function, so it's a maximization problem. But what makes it a standard problem in standard form? Well, a couple of things here. 2, I suppose, is I have non-negative constraints. So 1 is I want to maximize something. 2 is I have these non-negative constraints. Non-negative constraints. 3, all my inequalities, they're all of this less than or equal to form. So I need this as well. 3 is they're all less than or equal to inequalities. And there's actually one more thing here. 4, let me use a different color. Everything on the right-hand side of the inequality, all of those numbers are non-negative as well. So 4, all of these are bigger than or equal to 0. So I wouldn't be allowed to have, say, negative 12 here or negative 30. Whatever's on the right-hand side of that inequality has to be a non-negative number. But as long as I'm looking at a problem of this form, so all 4 of these things are satisfied, this is called a standard maximization problem in standard form. And again, I want to point out that our geometric approach from last time wouldn't really work here because I have 3 variables, and last time we were working with just 2 variables. So this section, 6.1, is actually fairly long. I'm going to brush over most of it. If you were to read through the textbook, you'd see stuff talking about the table method and so on. I don't want to get into the table method. It's not going to show up in the homework or anything. It's sort of just a prelude into the simplex method that I don't think we need to cover. There's also a whole bunch of terminology in this section. I'm going to again brush over all of that terminology, except for one little piece, which is I systems and E systems. So what I have right here, this is what the textbook calls an I system. Think of I as inequality, so it's a system of inequalities, and this is my I system for this associated standard maximization problem. What we're going to do is we're going to convert this to a so-called E system. So we're going to convert to an E system. I for inequality, E for equality. So we're going to convert to an E system by introducing what are called slack variables. Okay, so what do I mean by this? Well, up here, so here's my first equation. I have an inequality. I'm going to convert this to an equality. So I've got x1 plus x2 plus x3. I know when I sum those three things together, I get something less than or equal to 12. Well, that means there's a difference between this and 12. How about I call that difference S1? And if I add that to this side of the equation, that difference would make it equal to 12. All right, so S1, S for slack. There's my sort of slack variable. It makes up the slack, it makes up the difference between these two things. So if these three numbers add up to something less than 12, whatever I need to add to make up the difference, that's what S1 is. And we're going to do the same thing with the other two inequalities. So I've got 2x1 plus x2. Usually you try to stack these by column. So S1, I'll say this is equal to 12. So I've got no x3s, I've got no s2s here, but then plus some other slack variable, right? It's not the same slack variable, it's a different one because this is whatever the difference is between this expression and 30, that's a different number. So 2x1 plus x2 plus some new slack variable s2, that has to equal 30. All right, this expression is less than or equal to 30, so s2 is just the difference between them that I have to add to make them actually equal. And then we'll do the same thing with the third equation, x2 minus x3 plus some other slack variable, s3, is equal to 5. And this is the associated E system, obtained by introducing these three slack variables, S1, S2, and S3 to each of the three equations. Fairly easy process, right? You just go ahead and you add associated slack variables to each, and you make them equal instead, because the slack variables are precisely the number or the value that makes up the difference. It's the slack. You'll notice, by the way, because these are strictly less than or equal to 12, less than or equal to 30, less than or equal to 5, and those are all positive numbers, the slack variables here are all positive, right? So just notice that S1, S2, S3, I shouldn't say positive, but they're non-negative. They could be 0. All right, so that's I think that's all I really want to talk about in section 6.1. Again, there's a lot more terminology in the text. There's the table system, or the table method for solving these systems. But we're going to jump straight into the simplex method. And it turns out just this little piece right here, converting an I system to an E system, will be our first step always. So yeah, we'll move on to 6.2 right now.